And the very last thing for bonding is called orbital overlap and hybrid orbitals. And this is how do we actually bring areas of electrons together? And what we find is that they hybridize. And you guys are lucky because this is the last year that this is not a huge thing on the AP test. For right now, it's kind of a minor thing. You need to know it. They're probably going to ask you 1 or 2 questions on it. But next year, it's going to get enormous. So we'll just see how it goes. So the first thing we're going to talk about is valence bond theory, and basically just says, okay, like how do these electrons happen? So what happens is when you have different orbitals, usually they don't actually line up right. They don't have the right energies. They're not in the right orientation. So it's hard for them to come together. So there's a couple situations where it's pretty easy and it works pretty well. So one situation is where you have like the same element. So if we have hydrogen and hydrogen, well, they have the exact same electronic makeup and they're the exact same energy. So when they come together, you have a nice overlap here. So this is an s orbital, this is an s orbital, same energies, same orientation. They come together, and that's your orbital. That's your bond. You can have situations where the S's and the P's come together as long as it's the correct P. So depending on if it's PX, PY, PZ, thinking that there's 3 different directions for P's, sometimes they work as well. But it gets complicated really fast. And what valence bond theory deals with is just basically like how do they come together. So hybrid orbitals are what happens when, how many bonds do I need, and can as an atom, can they actually kind of mash them together to make them better? Because what we don't want to have is you don't want to have an s orbital with one energy and then p orbitals with different energies. Excuse me. So for example, say we're going to have 4 bonds. So say this is methane down here, carbon and 4 hydrogens. The carbon has to have 4 areas that can bond. So if you think carbon has 4 valence electrons, it has 1 in its S. Or I'm sorry, it has an S, 2 S's and 2 P's for carbon. What it actually does is they actually mix orbitals together. And what they find is instead of having an S area and P areas, what they do is they mix them together so that they're all exactly the same energy. And what you see is you have 1 S going in and 3 P's. So what you get is each of these are called an sp3 because you have everything mashed together. And then what happens is when you have your tetrahedral here, they're all exactly the same energy. So not one is better than the other one. And again, the reason you do this is because you want the same energy. This is very high level. This is something, again, in your book, online, you got to look it up. You have to read it. So then here's another one down here. We have ethene, double bond. So what we have here is we have a carbon double bonded, whatever. We're looking at the carbon that's wrapped in green here. So what you're looking at is you're looking at how many areas. So again, the double bond counts as an area. A triple bond counts as an area. So what you see here is this carbon has 1 area to a hydrogen, another area to a hydrogen, and another area to the carbon. So there's 3 areas. The first orbital you always start with is an S, and then the second ones you go to are always P's. So since we need 3, we take an S, which is 1, and we're going to take 2 P's. So what this guy is called is that he has a hybridization of an sp2. The S counts as the first one, and then I have 2 P's. And this is always your order. First bond is an S, second bond is a P, third bond is another P, fourth bond is another P. If you get into hypervalence, you would do D's, but the AP is no longer asking you about D's because there's a question of if that's even correct anymore, if D's can be involved or not. So you'll only ever go up to 4 bonds with hybrid, which is kind of nice. Here's just some examples here. Again, we kind of already did this one with the methane, but again, we have the carbon. It has 4 areas, 1, 2, 3, and 4. So we have, first one is an S, second one's a P, third one's a P, fourth one's a P, which is why he's called an sp3. If we look over here, this is a hypervalent thing. Again, they're not going to ask you that. And again, like in college, it depends on who your professor is, if they'll believe it or not, because they are fighting about it right now. This guy has 1, 2, 3, 4, 5. So you count 1, 2, 3, 4, 5. And that's why he's sp3d. And the last one right here we hadn't talked about is the ammonia. And what you have to worry about is, for valence bond theory, all things count. So we have 3 bonds here, they count, and the lone pair counts. So we have 1, 2, 3, 4, which means that we have to do the 1, 2, 3, 4, and he would also be an sp3. So it's not really hard, and then there's actually a little chart in your packet here, and I'll come back to the last page here, and it shows you which ones are which. But you do need to know, if I say, hey, what is ammonia, you need to know that it is an sp3 and that there's 4 hybrid orbitals going on. And if I say, BF3, you need to know, oh, that's sp2 and there's 3 hybrid orbitals. The last thing we're going to talk about is basically, okay, we kind of have skirted around single bonds and double bonds and triple bonds. So the last thing we're going to do is look at, okay, how do they actually form? So we have sigma bonds and pi bonds. And sigma bonds are ones that are between the nuclei. So if you look at this carbon and you look at this carbon, this purple bond in the middle here is a sigma bond because it's right in between the nuclei. These are your stronger bonds that form if you look at them just alone, and they're your single bonds. For any other bonds to form, we can't bond in the central atom anymore. We have to go somewhere else. So what we do is we go outside of it. So what happens is we have pi bonds, and this is when you have a double or a triple bond. So you always have a sigma. Every bond that there is in the world has a sigma. Every bond that there is, there's at least one sigma. But if you have more than that, you can have pi's as well. So if you look at this double bond right here, you can imagine that the top one is a sigma. That's the first one that forms. And that means that the bottom one is the second kind, and that means that there is 1 pi bond. And 1 pi bond looks like this above and below. And it has to do with p orbitals being connected. These are weaker bonds. They're not as strong as a sigma bond, but they do form, and they add extra strength to a sigma bond. If you're looking at a triple bond, you can think that first one's still your sigma, because you have to have a sigma bond. And then there's 2 left, so then that means a triple bond has 2 pi bonds. So if you're looking at this guy right here, this is ethylene. And ethylene has a double bond here, so let me try and draw him so that you could actually see him. Yeah, I'll draw him in red. So this is ethylene. And the question is, how many sigmas and how many pi's? So all single bonds are definitely sigma. So 1, 2, 3, 4. And then whenever you have a double or triple bond, one of these has to be a sigma. So we have 5 sigmas. And then because of the double bond, we have 1 pi. It's okay if you have no pi's. Like, you don't have to have pi bonds. But you have to have sigma bonds. And then just an extreme case of pi bonding is when we have that resonance effect. And what happens, the classic example is when you have that good old benzene, and you have that where you can draw like double, single, or single, double. What happens is the pi bonds get smeared the whole way around the whole molecule, which makes that benzene like a freak of nature that it can do this because of the different resonance structures. So whenever you have those resonance structures, that's what you're dealing with, the delocalized pi bonds, because they're no longer in a local area. They can be spread out. Again, this is your thing here. This will help you to remember some of your major angles, because you should know that a linear bond is 180 degrees. You should know a trigonal planar is 120 degrees, stuff like that. And then this will also help you with your hybrid orbitals and what's what. And then this last thing I'll just leave you with is just, oh, I think actually we already did this. These are just some polarity things if you want to look at those. So you have a lot of topics in this chapter. They're all new. Most people like this chapter, but it is a lot of kind of wrapping your head around stuff that you've never thought of before.